Okay, this is my second take tonight. I actually recorded a take and found out towards the end that I wasn't sharing my screen. So I am going to go through and verify that I'm sharing my screen, okay? And that I can be heard, so the audio is on. And so the recording is taking place, right? It says this recording. Okay, let's go ahead and finish up this chapter. I do hope my iPad holds because I've been at this for a couple of hours. Okay, so picking up where we left off, this is going to be chapter 15, part 3. Chapter 15, part 3, okay? We're starting with the 5% rule. So the 5% rule works this way. It's conditional, right? So most of the constants that we're going to be dealing with, equilibrium constants, we're going to call them EQ, these tend to be small, okay? Some are large, but they're usually small. When I say small, I mean like the value would be like 1.0 times 10 power negative 7, that kind of small, less than 1. So if and when your equilibrium constant is very small, the position of the equilibrium tends to favor the reactants. So if you have a small equilibrium constant paired with a reactant with a high concentration, because that type of reaction tends to be reactant favored, then when you have those conditions, you can actually approximate this expression here to 0. So the minus a, where a can be any number, so let's say minus 3x, would be approximated to 0. So you're probably wondering, why do we want to do something like that? And why is this even important? Why is there a 5% rule? Because of trying to avoid mental fatigue. Okay, at some point, we will have to do a quadratic equation. We don't want to have to do that all the time if it's not mandatory. If we're dealing with a very, very dilute solution, we can avoid the quadratic equation if we can show that taking the equilibrium constant, dividing this by the initial concentration times 100 will yield a percent that is less than 5, okay? So if we can show this, we can go ahead. Okay, hold on a second. If we can show this, we can go ahead and ignore the a minus x part that will guarantee a quadratic equation, okay? So let me go ahead and focus here, and then we can finish up this chapter. Okay, let's see. So once again, the 5% rule is conditional, right? So for relatively large initial concentrations of reactants, the reactant concentration will not change significantly when it reaches equilibrium. For that reason, once again, take your Ka value or your K value, K equilibrium, over the concentration of the reactant. So let's say reactant concentration here, multiplied by 100. If you get a number that is less than 5%, the approximation can happen. So let's go ahead and see how that works out, how this plays out in the problem. I'm going to start with this problem right here. So I actually went ahead earlier and copied it over. We have our balanced equation, equilibrium equation. We have our constant right here, Kc. We have the temperature. Remember, the constant depends on temperature. I think I mentioned this before. Now we'll draw our ice table because this question wants us to find equilibrium concentrations of the products, right? Okay. In our ice table, we generally, not all the time, for the most part, our ice table tends to have numbers presented as molar amounts, okay? So we tend to have molar amounts in here. Okay. This time, we're given moles and then liters. Remember, molarity just stands for moles in 1 liter. We have moles, but we don't have moles in 1 liter. So we're going to take our moles, 0.0125 divided by 0.50 liters. Therefore, moles per liter is the same thing as molarity. So I'll try to use my calculator here. Oops, I think I had something else here. So I did some different math. 0.0125 divided by 0.5 gives us 0.025. So this is going to be 0.025. I will write that over here, 0.025 m molar. That would be our initial concentration, right? because it has to be in the units molar. Most of the time it's in the units molar. The only time when it's okay to put in the units moles is if we know for sure it's over 1 liter. Okay? So you put 0, 0 here because the initial amounts of the product was not given to us. We only had reactants. Will the products always be 0 for this chapter? Yes. In the future chapters, I will let you know when it's not 0. Okay. In terms of x, remember the coefficients of x matches the coefficient of the formulas in the balanced equation. So here, this would be minus 2x, right? Because we have the amount of x reacting here. And to maintain that mole ratio of 2 to 2 to 1, we say here, if 2x amount of H2S reacts, then 2x amounts of H2 gets formed, and then x amount of S2 gets formed. So here, this would be plus 2x because products are being formed, they're increasing. This is going to be plus x. So at equilibrium, in terms of x, we have x of S2, 2x of H2, and then 0.025 minus 2x of H2S. Since our goal is to solve for the equilibrium amounts, we're going to go ahead and find what x is, plug it back in, and of course solve for it. Okay? Let's see how that plays out. All right, here, Kc is equal to, write out your Kc expression. H2, we have the product here, right? Raised to the power 2 times S2, raised to the power 1. The 1 is applied here. Sorry, I'm yawning. It's late. H2S raised to the power 2. Okay? Now, before we plug in the numbers in terms of x, actually, let me go ahead and plug in the numbers. Let me just get it over and done with. 1.67 times 10 power negative 7, 1.67 times 10 power negative 7 equal H2 will be this number right here, right? So we got 2x squared. S2 is going to be x divided by this one here, squared, 0.025 minus 2x. And then square that. Now, remember, our goal here is to apply the 5% rule. So, our 5% rule says 1.67 times 10 power negative 7. And our initial amount was what? 0.025 times 100. So, let me go ahead and divide this by 1.67 exponent negative 7, close parentheses. Okay. So I did the inverse of what I want, right? So for me to flip this over, I'm going to make it power negative 1. And that will give me the answer in the right format. Yeah. So this is giving us a very small number, 6.68 times 1, 2, 3, 4, 5, 6 times 10 power negative 6. This is definitely less than 5. Okay. That is less than 5. I didn't feel like deleting the number and then having to remember. So I just usually do the if I'm working and trying to divide some numbers and it's somehow the inverse of what I want, I go ahead and proceed, get my answer, and then flip it back up. Okay. Okay, so this is gonna work. It passes. Woohoo! Okay. So I'm gonna copy this over and you will see. So we have 1.67 times 10 power negative 7 equal over here. Let me distribute this part here. It becomes 2 squared x squared times x over. Oh, since the 5% rule passes, I can scratch this out. Only scratch the variables that are subtracted or added to a number, as in like 1 plus x, you can scratch this off. But we cannot scratch off 1x because it's multiplied. So only variables that are added or subtracted from numbers. Okay. And as you study this, it'll make more sense, or at least you'll be more familiar with it. So the bottom number becomes 0.025 squared, right? .025. Let me square this square. Okay, so my bottom number here becomes 0.000625, 1.67 times 10 power negative 7 This gives us what? 4. And then this gives us x cubed. So I'm going to take the bottom number times this, right? This is going to be 1. Cross multiply. I do this part first. I get 4x cubed. And I do this part second. And I still have my number from here. I'm just going to multiply by that number. Okay. So over here, I take this number that I still have in there, multiply by open parentheses, 1.67 exp. That's what this number is. Power negative 7, close parentheses. 1.044 times 10 power negative 10. Ah, okay, the yawning, man. It's getting real because the energy is low. Okay, so divide this by 4. Divide by 4, what do we get? 2.61 times 10 power negative 11. And then find the cube root. So 1/3 of this cube root, 1/3. Okay, so it's going to be power 1/3. So it's going to be parentheses 1 divided by 3. That's 1/3 of the fraction. And that should be equal to. Okay, so x, this cancels out here. That's how it works in math. 3 cancels out. X is equal to 2.97 times 10 power 1, 2, 3, 4, negative 4. Okay, so go back here. When you double that, okay, let me see. For this one here, let me record it right here. This is 2.97 times 10 power negative 4. And then let me double that to get the other number times 2. And I get 5.93 times 10 power 1, 2, 3, 4, negative 4 also. Okay, let's see what we get with this one here. Since I'm going to be taking this and adding it to this, let me try to make this number here negative. So I'll multiply by -1 to make it a negative number. Okay, so all I have to do is add this number to this, since this is -2x, right? So add 0.025 to that number. And I get 0.0244. Okay, this is molar, molar, molar. Let's see what they get. Okay. So we got, yep. So our answers are pretty similar. Our answers are pretty similar, right? Because it's 297 is what they got. Okay, 297. Let me try to bring my energy up a little bit. Okay, so moving on, we are going to practice another problem that has to do with the 5% rule, because I'm going to give you guys a little bit more practice before you get to your homework and, of course, the exam. Okay, so this problem here, the balance equation was not given to us. Well, it's mostly because I made it. Well, I didn't really 100% make the question up, but I found it online somewhere. So BR2 plus I2 produces 2BRI. Okay. Well, I guess I have to write it like this, right? 2IBR. I'm trying to copy this format here. Okay. We're giving initial amounts of the reactants. So we have initial, we have change, and we have equilibrium amounts. So let me go ahead and put this here. Our initial amounts are 0.5 molar and then 0.4 molar. This initial amount was not given. Our K value for this reaction is 7.1 times 10 power negative 10. Okay. So in a problem like this, you want to find out if the 5% rule works. So I'm going to try to put it here. 7.1 times 10 power negative 10. I'll divide it by the smaller number, okay? So 0.4, because if there is any number that's going to be dangerous, it'll be the smaller number, the one that's not as concentrated. Okay, so I will take, let me see, AC here, open parentheses, 7.1 exponent negative 10, close parentheses, divided by 0.4. It looks like it passes, right? Times 100. Usually, if your number is 1.77 times 10.87, if your Ka is -5 or if the Ka is some number power -5, if this number up here is -5 or smaller, the 5% rule tends to pass. Does that make sense? Once again, excuse the energy. I'm trying my best. I'm trying my best to stay awake. Okay. So let's see. Let's go ahead and do the reaction in terms of X. So to match the stoichiometry here, X amount of Br reacts, X amount of I2 reacts, producing 2X amount of IBR. Okay, according to the balanced equation. So according to that, we have 0.5 minus X at equilibrium, 0.4 minus X, and then 2X here. Okay, so let's solve for X. We've already figured out the 5% rule passes. Woohoo! So our K here is equal to IBR, close parentheses, square, and parentheses, yeah. These are brackets, so not parentheses. BR2, I2, right? We know the 5% rule passed, so we can actually approximate that part there to 0, that part there to 0. Leave this one alone because the X is neither added nor subtracted, right? So for here, when you plug in the numbers, K will be 1. Oh, no. Plug in the original K. 7.1 times 10 power negative 10 is equal to 2x. We're going to square this number divided by 0.5 divided by 0.4, right? So let's multiply 0.5 by 0.4. 0.5 by 0.4 equal 0.20. So essentially we have here 7.1 times 10 power negative 10 equal, distribute this part here, 2 squared x squared over 0.20. Cross multiply, right? Because this is going to be 1 down here. Ends up being 4x squared equal 0.20 times 7.1 times 10 power negative 10. Okay? Times 7.1 exponent negative 10 close parentheses. Okay, this 4x squared equals 1.42 times 10 power negative 10. Okay, divide both sides by 4. Divide by 4. And then once I get that number, this is x squared, right? 3.55 times 10 power negative 11. Now we want to find the square root of that. So take the power 1/2, and this one here will be power 1/2. So exponent, open parentheses, 1 divided by 2. That's how we get half. Close parentheses. And our answer ends up being x equal 5.95 or 6 times 10 power negative 1, 2, 3, 4, 5, 6. Negative 6. Go back and plug in the numbers in here. When you double that number, you get 1.19 times 10 power 1, 2, 3, 4, 5 power negative 5. And then divide by 2 to get our original number, right? Is that our original number? 5.96. Okay, yeah, that's it. And then for this one here, you take, multiply by -1 to make it negative, and then add it to 0.4. 0.3999, right? Which rounds up, you can see that because of significant figures, to 0.4. Okay. So let me subtract the 0.3. I mean, sorry, 0.4 again to get my original number. That's the original number that I had. Add this to 0.5 and we get 0.4999, which once again rounds up to 0.5. So hopefully you can see, right, how the significant numbers helps us to get the original and justifies our rounding off of the X value here, especially when the K value is very, very small compared to the original concentration. Okay, so we apply the 5% rule again. So we're moving on to Le Chatelier's principle. Le Chatelier's principle reminds us that the goal of the reaction is to get to equilibrium and stay at equilibrium, right? So Le Chatelier's principle tells us how we can disturb the reaction that's already at equilibrium and how the reaction will respond. So for every move we have, which our move is disturbance, there is a counter move from the reaction that will be trying to restore equilibrium. Okay. So the closest thing I can say to equilibrium in biology will be homeostasis, trying to maintain status quo, right? So you are going to disturb a goal that has been achieved, and then the system will react to restore that goal. Okay. Once a reaction is at equilibrium, its goal, the concentration of all the reactions and products remain the same. Okay. That tells us we are at equilibrium. However, if the conditions are changed by who? By us, the concentration of all the chemicals will change until equilibrium is restored, trying to restore or maintain status quo. The new concentrations will be different, but the equilibrium constant will be the same unless you change the temperature. So the equilibrium constants they've been giving us so far has been tied to temperature. Those constants were obtained when the reaction was done at that temperature. To change the constant for the same reaction, you have to change the temperature. That's what that's saying right here. The Chatelier's principle guides us in predicting the effect various changes in conditions have on the position of the equilibrium. It says that if a system is at equilibrium and is disturbed, if a system at equilibrium is disturbed, the position of the equilibrium will shift to minimize the disturbance. So for every move you have, the system has a counter move. Okay. And the counter move is trying to undo your move. Okay. So I wrote here overview. There are 5 major ways to quote unquote disturb the equilibrium. Okay. One of the major ways is by adding more reactants when we already at equilibrium. So we already achieved equilibrium, right? And the system would rather you don't do anything, just chill. You add more reactants. So now we have excess reactants. When you add more reactant, what the system does is it shifts right. Okay, why does it shift right? It's trying to get rid of the excess reactant that was added. So the only way to do it, to respond, is to react out all the extra reactants. Second thing you can do is remove reactants. Since all reactants have to be present and products have to be present, if you remove some reactant or all of a reactant, the system will panic and shift to the side where there's a deficit. Since the reactant is left, it will shift left. Why does it do that? It tries to restore that which has been lost to maintain equilibrium. So it shifts towards the side that has less reactant or product. Okay. I think I said 5 major, right? Well, by me breaking this up, technically these are equal to 1. How about that? So let me label this differently, okay? Because the way I labeled it is it's going to make this part here very long. I'm trying to itemize. So let me change this labeling here. I'll make this A. So 1A, 1B. How about that? When we are adding or removing a reactant, we're pretty much changing the amount of reactant. Number 2, to A, add more product. If you're adding more product now, you have excess product, so the reaction will shift left to get rid of the excess product you added. It can't just dump it out. We've never seen a reaction where chemicals just got dumped out deliberately, right? So the way it gets rid of something it doesn't want is just by processing it. It's kind of like metabolizing it. Only this time it's just going to process it by using it up, right? And in the process, it creates more reactant and then less product. But here we're going to have to be remove product. When you remove product, the system panics and shifts right, because now the right side has a deficit. You have a product that you have less of, so it tries to shift right to create more of the product. So what I'm putting in parentheses is the response. Response, okay. And then what I brought right here is the stress or disturbance. So how you can disturb, and then what how the system responds. Okay, so this is number 2, and we have this right here. My handwriting is getting messed up. Okay, number 3 is we can change the temperature. Change. Okay, so with this one here, let me just break it down like I did. 3A. For this part here, you have to specify if your reaction is endothermic or exothermic. Change in temperature will only affect an endothermic or exothermic process, okay? So I'll say here, for exothermic, remember exothermic reactions, heat is exiting, right? So let me answer 3A and 3B for exothermic reaction. So for exothermic reaction 3A, the reaction looks something like this. Let's say, let me give an example. The more I'm writing, I'm thinking about it, the more I'm developing this. So let's say we have H2 plus O2 to give us H2O, like that. And we have an exothermic reaction, so heat is released. So for that scenario there, increasing temperature, treat the heat like it was a chemical. So when you're increasing the temperature, reaction shifts away from the increase, shifts to the left, to the other right, to the left, right? Because you're increasing this side, so it has to shift to that direction. And then 3B, for the same type of reaction, when you decrease temperature, causes the reaction to shift to the right towards the area where you have the deficit. So shifts right, because now you have a deficit, so it's trying to make up for that deficit. So if you have a deficit, it shifts towards the deficit. If you have an excess, it shifts away from the excess. Okay? And so that's how this plays out right here. Okay, so the next thing I'm going to talk about here is I'm going to talk about the volume. Okay? So in the volume, I want to stick with the same problem here. 2H2 plus O2, and then we'll go with this. So I want to start with the volume and then talk about pressure. Okay, for this kind of problem here, we want to go back to 1411 and look at Avogadro's law. In 1411, by Avogadro, essentially, his law summarizes the relationship between the number of moles of a gas and the volume. And he said when you have a number of moles of a gas, you're going to need a greater volume. Okay? So there's a direct relationship between the number of moles of a gas and the volume that the gas will occupy. That makes sense. It's like more people, bigger space, right? Greater moles of gas, greater volume. So when you're going back to 1411 and looking at that, then let's look at it this way. When it comes to the equilibrium reaction, if you somehow increase the volume, so increasing volume, this scenario here, shifts the equilibrium towards, equilibrium reaction towards the side with more moles of gas. Okay. So greater volume then prefers the side that has more gas molecules. So here we have 2 moles of gas. So we'll say less, small volume. And this one here has got 3 moles of gas. So we'll say this one here is more, right? And therefore, this side here wants a higher volume. So for our equilibrium here, if we increase the volume, we're going to shift the reaction to the left because the left side tends to have more moles of gas. Does that make sense? So increasing volume shifts the equilibrium to the reaction towards the side that has more moles of gas. In our case, that's going to be to the left, to the left. I'm not going to start singing. No. Okay, let's go on. And look at one last concept. Of course, doing the opposite, right? Decreasing volume shifts reaction to the right. So I'm going to say to the left. Okay, we're going to go with our last stressor, right? Our last stressor will be pressure. So let's stick with the same reaction, right? We got 2H2 plus O2 to give us 2H2O. Once again, we got 2 moles of gas here. Here we got 3 moles of gas. So the way pressure works is you actually start with how pressure influences volume. So even though our goal is pressure here, this question can be asked to you differently, 2 different ways, One way can say increasing pressure, period. Okay? This is what I'm going to address right now. Versus if they say increasing pressure of oxygen. If they say increasing pressure of a particular gas, that's telling you something completely different. If the question says increasing pressure of oxygen, for example, just increasing this amount here, it implies that everything else is kept constant, right? In that case, treat the one on the right as amount of oxygen. So if the question is stated this way, treat that question as though they're saying only oxygen is increasing and nothing else is. How does the whole system respond? Because you change only the amount of one chemical, not the amount of all the chemicals or the environment, right? In that case, of course, changing oxygen, the reaction was shifted to the right away from the increase, right? But what I'm showing you here in this problem here, as I said, I am focusing not on changing just the pressure of one chemical. I am focusing on increasing the pressure, period. So I'm going to erase this part here because this is what we're focusing on here. Increasing the pressure. So the pressure of the whole container or the pressure outside the container. Let's go back to 1411. In 1411, we learned Boyle's law, right? The summary of Boyle's law statement said, when you increase pressure, so a higher pressure results in a lower volume. So you want to go back to 1411 and remember that. So we have an inverse relationship between pressure and volume. So higher pressure results in, this is high pressure, results in low volume. Of course, we're talking about external pressure, right? Not the pressure of one gas. And because of that, if we have low volume, we need, less moles? So high pressure goes with low volume, and that demands low moles of gas. So increasing pressure decreases the volume resulting in the equilibrium shifting to the right. Okay. And vice versa, right? If we decrease pressure, the volume goes up. So if you lower the pressure, that results in the volume, increase in volume. And then this causes the reaction to shift to the side with more moles, which in our case, that would be to the left. Okay. Okay, so if these are the things that affects our equilibrium, what doesn't, you ask? Oh, I'm just going to tell you right now because I'm just giving you guys the bottom line, right? Then we'll go through the slides and finish up the chapter. So what doesn't affect equilibrium? The following items do not affect. Let me give them some respect and give them a whole page. These items do not affect equilibrium. So I'm gonna actually give them a whole page. It doesn't require a whole page, but these changes or disturbances do not affect equilibrium. Okay. These are number one, adding an inert gas. Inert gas does nothing because inert means doesn't react. Okay. Number two, adding a solid. Remember, solids don't change significantly to affect equilibrium, so nothing happens with that. Number three, adding a liquid. Once again, this is nothing towards your equilibrium, so nothing. And then what was the last thing again? Oh, yeah. Adding a catalyst, okay? Does the catalyst affect the equilibrium? It affects how fast we get there, but not really the value, okay? It affects both the forward and the reverse reaction equally, so we get a wash, no change, okay? So the following changes, once again, do not affect the equilibrium, adding inert gas, adding a solid or a liquid or a catalyst. Okay, now that I've covered that part, we can then just go through this part. As they're saying here, if you increase the amount of the reactants, it will increase. Sorry, if adding a reactant will decrease the amount of other reactants and increase the amount of the products until a new position of equilibrium is found. So for this part here, I'm not gonna just go through this and then try to read everything. That would be a little bit boring. I'm kind of giving you guys the overall, right? Equilibrium shifts away from the side with added chemicals towards the side with removed chemicals. What I want to talk about here is sometimes the questions don't come out as simple as it's being communicated here. Sometimes the questions are a little bit more complicated. So let me try to give you guys an example. Okay. For this part here, I'm going to try to use the visual. I'll say A plus B reacting to give a B. This is our equilibrium that we're working with. Let's say that when we are at equilibrium, I'm going to define equilibrium terms. Let's say this is at equilibrium. So this is how I'm abbreviating. At equilibrium, you know what? Let me try to mix this up a little bit. I make the B blue. Wait, why is B not blue? I make B, touch this. Okay, there, blue. Okay. So we'll say that at equilibrium, it takes 1, 2, 3, 4 of this, okay? And then let's see for this one here for A. So this is at equilibrium. So at equilibrium, now remember, equilibrium doesn't mean that we have equal amounts of the chemical. So just to make a point, I'm just going to leave it like this, right? Equilibrium doesn't mean that we have equal amounts of chemical. Equilibrium means we have constant amount of chemicals because the rate of forward matches the rate of the reverse. So since I'm trying to make that point, let me try to just make these different on purpose because I don't want to miscommunicate. Equilibrium means equal amounts. Equilibrium means equal rate. The speed to go in the forward, it matches the speed of the reverse. So the speed of the forward matches the speed of the reverse, not the amounts. So the amounts of the reactants don't match the amount of products. So to make that point, I am sticking with different amounts. Let's see how this plays out. If it doesn't play out, I'll just do something else. Different color. Okay, different color. Sorry. Right here. So we have 1, 2, 3, 4, 5. Okay. So let's say that this is defined as equilibrium. This is the picture of equilibrium. Okay. Equilibrium happens when we have 3 A's, 4 B's, and then 5 ABs. That's equilibrium. So I come over here and I say, oh, I am going to stress this. I'm going to disturb this. I'm going to bring about a change or a disturbance. My disturbance is I am going to add, let me add some B. I'm going to add, so the disturbance will be to add, okay, so add these 2 circles, so 2 amounts of B. Can we handle that? Yeah, I think we can handle it. So by me adding 2 amounts of B, what I've done here, maybe I feel like 2 may be too much. Let's just add 1, okay? I'm just going to add 1 amount of B right here. So in doing that, then this is what the change does. So now we have 5 B's instead of having 4 B's. This is how the system is responding, right? It hasn't responded yet. This is me just applying the change. So I didn't change the amount of A. A is still 3. But now B has that extra amount added. Let me see. Tap that. This right here is now the extra, correct? The response has yet to come out. I'm acting as though the response is like a track. It's not like a diss track or something. No, it's like I am curating my response. But essentially, the system has to respond. It has to be a counter move. For every move, is a counter move. So it hasn't responded yet. Oh my goodness. Oh my goodness. Okay. Okay. Let me start this part over. Okay. So So let me go ahead and show you guys what the disturbance is going to be. So our disturbance, I will add an amount of B. So I'm going to add 1 amount of B. That will be my disturbance. So I add this amount. This is 1B. Okay. So I'm adding this. Essentially, I'm adding a reactant. We know the reaction will shift away from the axis, right, towards the right side. Okay, but let's see what that looks like. So this is where I started. This is at equilibrium, and this is the disturbance. This is showing the disturbance. And in my disturbance, I only change B. So the B is the only one that's changed, right? Went from 1, 2, 3, 4 into having a fifth one. So this is the extra. Okay. I haven't done anything with my product. So, oh, no. I hope it doesn't die. Let me hurry up. I haven't done anything with my product. So I have 1, 2, 3, 4, 5, right? And this is attached to, A, 1, 2, 3, 4, 5, right? And we have this right here plus A, 1, 2, 3. So I'm showing you the only one that has changed. The disturbance is this part right here. How does the system respond? The system notices the extra, right? And tries to get rid of the extra. The only way to get rid of it is to react it out. But you can see the stoichiometry, right? It takes one of this to react with one of this to make the product. We need one from red, one from blue. So the way we react out the blue is to react it with the red. So in getting rid of the extra, we take away one of the reds from here, and the response is then you get one, and this goes with this to create this. This is our new one. So this right here is new. This is the response. So when everything is said and done now, I need one more page to publish the results. What happens? This is the system saying, I don't like what you did, so I'm going to work against you. So this is the new equilibrium. This is what it looks like. So I'm going to show you let me try to get back here. So we have A. A now only has 2 left, right? Correct? Because one got used to get rid of the excess B. So it had to sacrifice itself. Okay. Over here, we now have 1, 2, 3, 4, 5. That was the original. Then we have 6 from the new one, right? And now I'm going to show you B. B is back to having what? 4? Yes, B is back to having 4. This is back to the original amount. But now we have an extra AB. We have 1 extra AB and we have 1 less A. Hopefully that makes sense. So this is our new equilibrium. And that's what we mean by shifting right. It now prioritizes moving to the right, but there's still a reverse reaction. Remember, there's always going to be 2-way reactions in equilibrium. And this is what we say the reaction. This is what we mean when we say the reaction is shifting to the right. Okay, let me go ahead and show you how this plays out then. Since I've shown you that part already, let's skip anything. Okay, I'm going to go through, answer these questions and finish up the chapter. So over here, we're told we have an equilibrium reaction. What is the effect of adding CO2? Since CO2 is the product, when you add this, it shifts to the left. And then what's the effect of adding CaCO3? CaCO3 is a solid, so the answer is nothing, no effect. Oh, I just thought about something. The other thing I showed in class was the seesaw analogy. Let me try that and see if that will work. The seesaw analogy is saying that equilibrium is balance, okay, balance swing. So here you have the reaction or reactants, and here you have the products. The reaction's goal is to be at equilibrium. So this is defined by the seesaw looking like this. So if you add reactant, right, you add reactant, it's like adding a weight to the reactant side. That results in the system shifting like this because now you have a heavier reactant, more reactant compared to products, right? Because the change was you added reactant. For the system to go back to equilibrium, it cannot just dump out some reactant. So it has to process it and use it by moving some chemical or by moving out some of the reactant and creating more products, right? So it's kind of like if it was a weight, you added more extra weight here, you move some of the weight to the other side. Let me see if I can make this play out a little bit better. Instead of using letters as R and P, let me use R and P on top of images. I'm really trying to improve my craft as I'm doing it and my explanation. So let me see. I just had an idea. Let's say equilibrium involves this amount here. So I'll put 3 here and I'll put 3 here. This is your reactant. You have your product. Then you add more reactants. So now by adding more reactants, we have 1, 2, 3. Let's say 4. Okay. This analogy may not work very well because it doesn't necessarily work like weights, right? It doesn't. Because whatever you add here, the system will actually work to remove everything you added, not some of it. That's why what I'm saying won't work very well, but it kind of removes everything you added. So when it does so, you get to a new equilibrium where we have 3 on the reactant side, but the additional amounts you added got moved to the product side, and we're now at a new equilibrium. Does that make sense? I know it doesn't make sense with weights. It makes sense with the chemical reaction, though. Whatever extra was added gets reacted out, not just half of it. So I feel like this analogy will not make much sense. So let's go back. Let's go back. Let me try the weight analogy that we talked about in lecture, okay? So we have a system at equilibrium. We have a reactant here on the left and the product on the right. And the system desires to be at equilibrium according to the Chatelier's principle. So if you add more reactant, what you're doing is creating an imbalance. Now you have more reactant than you do product, right? For us to restore the equilibrium, you want to shift the reaction away from the reactant since you have too much of it. That's why it's kind of weighted on that side. And then in doing so, you restore the equilibrium. So you went from here to here. But once you do the switch like that, the change to this direction here, and this takes you back to the equilibrium that you started off with. Okay. I'm going to do the opposite here and say, what if you remove a reactant? So let's remove reactant. Remove some reactant. Not all, just some. If you do so, it will actually raise the reactant part because now you don't have as much reactant that you had before, right? So for us to try to get the reaction to get back to equilibrium, you're going to go ahead and reverse the reaction, move it, shift it to the left to get back to equilibrium. Okay, so this results in the reaction getting back to equilibrium. You add reactant, it shifts away from the excess. You remove the reactant, it shifts towards the lesser part. And that's true for product also, okay? So if you add product, let me remove the arrows here, because now the arrows don't apply, right? I feel like I'm being lazy. Let me just erase all of this. Erase it all, erase it all. Just erase everything. And let me see if I can. Okay. So once again, the goal is balance, right? This time, if we add product, then we go from reactant product to product side being heavier because you have more products. Reactant side being lighter. So for us to get back to normal, we want to react because we have too much product. We want to react out some of the products, get it back to the reactant, and that will restore equilibrium. If we remove product, the product side becomes relatively less. Remove product. In this case, it's a little bit higher because you have relatively less product, right? You want to sacrifice some of the reactant side to create more product to get back to equilibrium. The goal is to make sure that at equilibrium, all reactants are present. Remember, I mentioned this before. If I didn't, I'm mentioning it right now. That if a reaction has got, let's say, 5 chemicals total, right? Oops, DE. You have 3 reactants, 2 products. At equilibrium, you need to have all 5 chemicals present, not in the same amount, but they all have to be present, right? So the reaction will always shift in such a way to replenish the deficit area and shift away from the excess area. Okay? But let's go ahead and move on. I described all this part here, so I'm just going to read the dark parts and say, according to the Chatelier's principle, when the volume decreases, the equilibrium shifts to the side with fewer gas particles. I've discussed that already. Let's answer this question here. I'm just going to go through and answer the questions. What is the effect of decreasing the volume of the reaction mixture? Oh, volume. Where are the gas molecules? Here we have 3 moles of gas. And here we have 0 moles gas, 0. So 3 moles prefers large volume. Or should I say maybe not large volume, maybe increased volume. Increased volume. And then 0 moles of gas, small volume. So what's the effect of decreasing the volume of the gas? Oh, it's going to shift to the left because that's when you can have a smaller volume or 0 moles of gas. Increasing the volume of the reaction mixture, it will shift it right because right prefers increased volume because you have more moles of gas. Inert gas does nothing. I already told you guys that in the beginning, right? When I gave you the recap. And you can go through and read all this stuff over here. I'm trying to just skim and get to the end. Ooh, so over here we have an exothermic example reaction. Treat heat like it's a product, like a chemical. So if you increase heat, this reaction shifts to the left. If you decrease heat, the reaction shifts to the right. So in our endothermic example here, if you increase heat, the reaction shifts towards the right. If you decrease heat, the reaction shifts towards the left. Okay? So I'm going to explain this part right here. This is usually experimental, right? So in the lab, the chemicals cannot tell you we are shifting to the left, or to the right, correct? So you have to rely on visuals. This experiment is a good one to do in the lab. We didn't do one like this. We did a different one. And in this case here, we have an endothermic reaction. How do we know? Well, if the reaction shifts to the right, we will see more brown. So brown is the same thing as shifts right. Okay. And then more colorless is the same thing as shifts left. Because the chemical on the left side, when it's formed, is more colorless. So we can see right here that this reaction is endothermic with the heat on the reactant side, exiting heat on the product side, right? We know this reaction is endothermic. Why? When you place the reaction in a cold environment, that's the same thing as saying when you decrease the heat, the reaction shifts to the left. That is consistent with endothermic reaction. And then over here, when you increase the heat, the reaction shifts to the right, making more brown. So this is hot water right here. This is hot, and this is cold, or you can say ice. Okay. So once again, here we're told the following reaction is endothermic. Add the heat to the reactant side. What is the effect of increasing the temperature? You increase heat, it shifts to the right of the mixture. Decreasing the temperature. You decrease heat, it shifts towards the decrease, left. This is also endothermic. If you increase, oh no, I was using blue for decrease, right? Because it's like cold. Brrr. Oops, wrong thing. Okay. So I'm at red now. Red is increase. So when you make it hot, it shifts away from the increase, right? And then when you make it cold, it shifts towards the decrease. I told you guys why catalyst provides alternative way to make the reaction go fast. Both catalyst works for both forward and reverse reactions. Therefore, catalyst has no effect on the position of the equilibrium. Okay. Oh, we are at our last question. Woohoo! Okay, let me stop celebrating and finish this question. So in this question here, we're dealing with an equilibrium, and it says it's an endothermic. Okay, increasing concentration of the reactant. Increasing this. Let me use red for increase. Okay, so increasing the reactant causes the reaction to shift right. So I'm going to write here right. Oh, they did say shifting equilibrium. The following changes shift the equilibrium to the left or right. So we have to say it. So I'm saying this shifts to right. Okay. Second one, decreasing concentration of NH3. So we're decreasing the product, right? For the second one. Let me erase it so it's not too crowded. When we decrease the product, it also shifts to the right because it's trying to replenish what's been lost. Okay? We can say like this, it replenishes what's been lost. Okay, next one, increasing pressure overall. Increasing pressure. The left side has got 3 moles gas. That goes with greater volume and lower pressure. The right side has got 2 moles gas, lower volume, greater pressure. The pressure and the volume are inversely proportional. Okay, so when we increase pressure, it will shift to the right because this prefers higher pressure. Increasing volume will shift left because higher volume goes to the left side. Increasing temperature. When we increase the temperature, it will shift to the right. Inert gas, nothing. Or no change. Add solid or liquid, nothing. Add catalyst, nothing or no change. You can say for this one here, no change. Okay. Okay, let's see what it says here. Right, left, right, no change, no change, no change. And with that, guys, we are done. I made it, persevered. Okay. Good night.